Hello all! In this video, I am going to talk about how the binomial distribution gets close to or approaches a normal distribution as n times p gets larger. Recall that n is the sample size and p is your probability of success. Or we could say n is the number of fixed trials and p is the probability of success. What you're seeing in front of you right now is a histogram of a binomial probability distribution where x goes from 0 to 50 and p of x can be changed by changing the value of p, the probability of success. Currently, we see that p here is 0.1, so that n times p is 5, because n is 50, p is 0.1, so we have 5, all right? Now, what you see here is a very right-skewed distribution. However, nearly this entire tail is virtually 0. So if we look at just this leftmost piece, we see it's actually very symmetric and very bell-shaped. All right. Now let's increase our probability of success to 0.2. Okay, now notice how the histogram shifted a little to the right, so a little less right skewed, got a little bit of a left tail there now. But again, notice how the tails are virtually 0. And we see here that this has become very symmetric, very close to bell-shaped when you look just at the non-zero part of the graph. And here we have n times p actually equals 10, because now we had 50 times 0.2. All right? And so it's at this point that we usually say we can use a normal distribution to approximate the binomial. Look how more and more normal the distribution gets as I increase n, and therefore n times p gets bigger. You see that the tails become more and more symmetric, although they're still close to 0 out in the ends, and the middle part is getting more and more symmetric and bell-shaped. Very, very close. Let's do 0.4 here. All right, and then you'll see as we get to 0.5, it is perfectly symmetric. And you could see that by looking at these probabilities over here as well. All right, so this just demonstrates how for large enough p's relative to n, the sample size, that our binomial approaches a normal distribution, hence we can use a normal distribution to approximate binomial probabilities. Now, in a light of powerful computers and software, it's not usually necessary to use a normal approximation to the binomial. However, knowing that the binomial can be approximated by a normal leads us to a nice conclusion about the sampling distribution of the proportion, the sampling distribution of the proportion, which is the same thing as a distribution of sample proportions. I'm going to move on to this next tab here, Inferential, because once we know about the sampling distribution, we can talk about inferential statistics and especially estimating. This is where we want to start with estimating. So what do we mean by estimating? Well, sample statistics estimate population parameters. Remember, sample statistics are values that come from sample data. Sample mean, sample standard deviation, sample proportion is what we're interested in here. And these estimate the population parameters like the population mean, the population standard deviation, the population proportion. Here we're going to be focusing on qualitative data, so we're going to be looking at proportions. Proportions are the same things as the relative frequencies. So here we have sample proportion, p hat, is a relative frequency. And this sample proportion is going to estimate the population proportion, p, which is the actual probability of success in a binomial experiment. So p hat estimates p. Our relative frequency will estimate the probability of success in a binomial experiment. So we can say the sample proportion estimates the population proportion. Well, that means our sample proportion is an estimator, but we want to be sure that it is a good estimator. So what makes a good estimator? Two things we need. We need to make sure that our estimator is unbiased and that our estimator is consistent. So what do we mean by unbiased and consistent? Unbiased means that all the possible sample proportions, all right, are actually centered about the true parameter, all right? So when you look at a graph of the distribution of sample estimators or the sample statistics, the center of that graph will be the true value or the population parameter. All right, so an unbiased means that the sample values are centered about the true value. Consistent means that for all the different possible sample values, they'll be close together. You won't have large variations, but they'll be close together or consistent. So when you have that, what you're really going to end up with is something that looks bell curved, all right, bell shaped. So here we see that we're getting this bell-shaped distribution. So we can say that the sampling distribution of proportions, which is a distribution of sample proportions, then is bell-shaped. So I'll draw it here, right? We got a bell-shaped distribution, all right? And it's a distribution of sample proportions. I mentioned that the sample proportion is called p hat. So the way that actually looks is p with a hat on top. And it looks like a little party hat, right? A little cone-shaped party hat. So this would be a distribution of sample proportions p hat. Now, so theoretically, right in the middle, we would have the true proportion or the population parameter p, all right? Now, because most of the data here is close together, right? It's consistent. We see we get the greatest frequencies here in the middle. And because it's unbiased, that's why it is centered around the population proportion. So we're going to have a normal distribution for the distribution of sample proportions. We will have a normal distribution or a normal sampling distribution. So any distribution of a sample statistic is called a sampling distribution. And the mean of that sampling distribution is the population parameter. That's how it will work. Then we're going to have the spread or the standard deviation of the sampling distribution. And instead of calling standard deviation, though, we now call it the standard error. So the standard deviation of a sampling distribution is the standard error. And as I was just showing you, the sampling distribution of proportions is normal. It is normal. Now, we can say it's normal when we have a mean and standard deviation. When we have the p and the sample size n times p be at least 10. But that also means n times 1 minus p, right? N times the probability of failure has to also be at least 10. And that's when then this is all valid. So this will be valid when these two requirements are met. So whenever we're working with then a sampling distribution of proportions here, all right, or we want to do some inferential statistics using a sampling distribution, we need to make sure that we satisfy the requirement that n times p and n times 1 minus p are at least 10. All right, that's pretty much like saying that you're working with a distribution where all of these frequencies really should be at least 10. Okay, so if we wanted then to do for sedans, okay, we can do it, it's at least 10. But if we wanted to do confidence intervals for the hybrids, and I'll talk about estimating. Confidence intervals is a form of estimating. If we want to do estimating for the hybrids, it really isn't going to be as accurate as it should be because we only have n times p is 9. Now, older textbooks, some textbooks will say you only need n times p to be at least 5. So if you have n times p be at least 5, then, we would do this, but you would get better results if your frequency is at least 10. All right. And in all the examples we do when we're going to be estimating proportions, we will be using data where x is at least 10. So that n times p ends up being at least 10. Okay, so back here then. So we have a sampling distribution that is normally distributed with the mean equal to the population parameter, which is the sample proportion, and a standard error given here. Now, where does this standard error come from? You just need to know how to use it, but I'm going to go ahead and show you where it comes from. And to do that, we're going again back to our binomial distribution here. So remember that when you have a binomial distribution, okay, the sample, or I should say the mean of a binomial distribution is actually this n times p, okay? So this is the mean this is the mean of a binomial probability distribution. Now, a binomial probability distribution has the random variable x, which you recall is number of successes. Okay, so the random variable x is the number of successes. What we want is actually a distribution of sample proportions. And remember here the sample proportion p hat, okay, the sample proportion p hat is a relative frequency, so it is x divided by n. It's x divided by n. So if we want a distribution of sample proportions, okay, then what we're going to have here is the mean here would be n times p. But then to get it to be a distribution of sample proportions where we have to divide by n, notice that when I divide this by n, the n's cancel out and I am left with a distribution with a mean of p. All right, so we start with a binomial distribution with a random variable x, number of successes. To change that into the random variable p hat, the sample proportion, we have to divide the x by n, which means now that the mean of the distribution of sample proportions will be the mean of the binomial distribution n times p divided by n, which gives us the p. And like we were saying over here, then that gives us the our sampling distribution with the mean of p. Well, I was first referring, well, how do we get the standard error? Because that wasn't even, this here doesn't come up just conceptually or intuitively like we thought about the mean of p from getting a normal distribution. We're all trying to estimate this population mean p, so we end up getting what looks like a normal distribution hovered around the true value, right? We saw how we can actually derive this starting with the binomial distribution. Well, we're going to also derive this standard error from the binomial distribution. So recall that the standard deviation, let me do it this way. Recall that the standard deviation of a binomial distribution, the standard deviation of a binomial distribution is the square root of n times p times parentheses 1 minus p, right? It's the square root of sample size times probability of success, which interestingly, notice that this here, n times p, that is the mean. So we take that and then we multiply it by the probability of failure, 1 minus p, and what is just underneath here, okay, what is underneath here, this whole thing underneath here, that would be the variance, right? That would be the variance. And so then when we take the square root of the variance, we get the standard deviation. Okay. So this then is the standard deviation for a binomial experiment. Standard deviation for a binomial distribution is the square root of n times p times parentheses 1 minus p. Okay, but now we want to divide this by n so that we can find the standard error for a sampling distribution for proportions. So the standard error here is going to be the standard deviation for that binomial experiment for a distribution of successes x, but to get it to be a distribution of sample proportions, remember, we divide by n to get x over n, which is p hat, the sample proportion. So what we're going to then need to do is take our square root of n times p times 1 minus p, and then we're going to have to divide this whole thing by n. Now, when you're dividing a radical or square root by n, and we want to take the n underneath the square root, then what we're going to need to do is when we put the n underneath the square root, it is going to become an n squared. So what we have here now is n times p times parentheses 1 minus p, okay? And then that's going to be divided by the n, but now it is squared. So notice if this is n squared inside here, then this n will cancel with one of those n's, and what you're left with is the square root of the p times 1 minus p over just 1n, and that's what we have over here. The square root of p times 1 minus p over n. So this then is the standard error for the sampling distribution of proportions. And you can think of, because it is, the standard error is really a standard deviation. So the standard error is the standard deviation of a sampling distribution. So the sampling distribution, okay, for proportions, which means it's a distribution of sample proportions, has a mean equal to the population proportion p and a standard error equal to the square root of p times 1 minus p over n. Right? And so what we have so far too is that p hat, actually let me write this down. What we have here is that p hat estimates All right, and that's our point estimate. That's our point estimate. So in the next video, I'm going to be talking about interval estimates, which will give us a range of values rather than a single value. And this way we can explain how good our estimate is, right? Because we can get a point estimate where am I having issues here? Okay, we can get a point estimate, which is a single value, but we want to know then how good is that point estimate? How good is that point estimate? And we're going to find that out by constructing an interval estimate. So the next video will be about interval estimates, or what we also call confidence intervals. All right, thanks for watching.